Cosmic Catastrophes: How Space Shaped Life and Extinction on Earth. The Illusion of Isolation. For most of human history, we have looked at the Earth beneath our feet and the sky above our heads as two distinct realms. The Earth was the stage of life, a stable platform where biology played out its drama of competition and evolution. The sky was merely a backdrop, a canvas of divine order or physical curiosity, disconnected from the muddy reality of survival. This geocentric perspective, while comforting, is a profound illusion. The history of our planet is not a closed narrative contained within the atmosphere. It is a violent, dynamic chapter in the history of the galaxy. Earth is an open system, porous to the influence of the cosmos. From the very atoms that make up our bodies to the water in our oceans, from the stable climate we enjoy to the mass extinctions that cleared the path for our existence, space has been the architect. We live in a cosmic shooting gallery, a universe teeming with radiation, flying mountains of rock, and gravitational tides that dwarf the power of any terrestrial volcano. To understand the history of life on Earth, we must understand the cosmic catastrophes that shaped it. We are not merely observers of the universe. We are the survivors of it. The violent Genesis and the Hadean Eon. The story begins 4.5 billion years ago, not with a whisper, but with a scream. The solar system formed from the gravitational collapse of a giant molecular cloud, likely triggered by the shockwave of a nearby supernova. This initial cosmic kick enriched the pre-solar nebula with heavy elements, gold, uranium, iron, forged in the hearts of dying stars. As the sun ignited, the remaining dust and gas coalesced into a protoplanetary disk. In this chaotic nursery, dust grains stuck together to form pebbles. Pebbles became boulders, and boulders smashed together to form planetesimals. The early Earth was born in violence. This era is known as the Hadean Eon, named after the Greek underworld, and for good reason. The surface was a magma ocean, the atmosphere a choking haze of vaporized rock and volcanic gases. It was during this hellish infancy that the most defining cosmic catastrophe occurred. A protoplanet the size of Mars, named Theia, was on a collision course with Earth. The impact was cataclysmic. It did not just crater the surface, it liquefied the planet. The outer layers of both bodies were blasted into orbit, forming a ring of molten debris that eventually coalesced into the Moon. This was not just a destructive event. It was the stabilization event. The Moon acted as a gravitational anchor. Without its stabilizing influence, Earth's axial tilt would wobble chaotically over millions of years, causing the climate to swing wildly between global freezes and boiling heat waves. Such instability might have prevented the long-term evolution of complex life. Thus, the collision that nearly destroyed the Earth ultimately made it habitable. The late heavy bombardment and the delivery of oceans. Following the Moon's formation, the solar system appeared to settle, but around 4 billion years ago, chaos returned. The giant planets, Jupiter and Saturn, likely underwent a migration, shifting their orbits. This gravitational dance, known as the Nice Model, disrupted the stable orbits of the asteroid belt and the Kuiper belt. The result was the late heavy bombardment. For millions of years, the inner solar system was pummeled by a rain of comets and asteroids. The scars of this event have been erased from Earth by wind and water, but the Moon remains a pockmarked witness. While this bombardment would have sterilized the surface, vaporizing any early protolife, it brought a gift. The Earth formed in the hot inner solar system, inside the snow line, meaning it was likely born dry. The water that fills our oceans today was likely delivered by these icy impactors from the cold outer reaches of the solar system. Alongside water, carbonaceous chondrites, meteorites rich in organic compounds, rained down, seeding the primordial soup with amino acids, the chemical precursors of life. It is a profound irony that the bombardment which made the Hadean Earth a nightmare also delivered the essential ingredients for the biosphere. The faint young sun and the greenhouse shield. Cosmic influence is not limited to physical impacts. It involves the evolution of our star. Astrophysics dictates that main-sequence stars like the Sun grow brighter as they age. 4 billion years ago, the Sun was approximately 30% dimmer than it is today. This presents the faint young sun paradox. If we input a 30% reduction in solar energy into modern climate models, Earth freezes over completely. Yet, the geological record shows ancient sedimentary rocks deposited by liquid water. The solution to this paradox lies in the atmosphere. The early atmosphere was likely rich in greenhouse gases, carbon dioxide and methane, far denser than today's. This atmospheric blanket trapped the meager heat of the young sun, keeping the planet warm enough for life to start. This highlights a critical point. Planetary habitability is a relationship between the star and the atmosphere. As the sun brightened over billions of years, biological and geological processes drew down the carbon dioxide, cooling the planet to compensate for the increasing solar heat. This thermostat, however, has broken several times, leading to snowball Earth events where the planet froze from pole to equator, likely triggered by fluctuations in solar activity or the passage of the solar system through interstellar dust clouds that block the sunlight. The Great Oxidation Event and the UV crisis. Life eventually became a cosmic force in its own right. Around 2.4 billion years ago, cyanobacteria evolved the ability to photosynthesize using water, releasing oxygen as a waste product. This was the Great Oxidation Event. For the anaerobic life that dominated the planet, oxygen was a deadly poison. But for the future of the planet, it was a shield. Before oxygen, Earth had no ozone layer. The surface was bathed in lethal ultraviolet UV radiation from the sun, forcing life to hide in the deep oceans or in protective slime mats. As oxygen accumulated in the atmosphere, it reacted with solar UV light to form ozone, O3. This stratospheric layer absorbed the most harmful radiation, finally allowing life to colonize the surface waters and eventually the land. The creation of the ozone layer was a chemical reaction between biological waste and stellar radiation, a planetary defense shield forged by bacteria and sunlight. Gamma-ray bursts and the Ordovician extinction. The first of the Big Five mass extinctions occurred 440 million years ago, at the end of the Ordovician period. While the immediate cause was a severe ice age, the trigger remains a mystery. One terrifying hypothesis is a gamma-ray burst, GRB. GRBs are the most powerful explosions in the universe, caused by the collapse of massive stars into black holes. A GRB directs a focused jet of high-energy gamma radiation. If a star within 6,000 light-years of Earth went supernova and pointed its jet at us, the results would be devastating. The pulse would last only seconds, but it would shred the ozone layer. With the shield gone, solar UV radiation would burn the surface. The radiation would also split nitrogen molecules in the atmosphere, creating nitrogen dioxide, a brown gas that blocks sunlight, triggering global cooling. The extinction pattern, heavy losses among surface-dwelling plankton who are vulnerable to UV, and a subsequent ice age, fits the profile of a GRB event. It serves as a reminder that a dying star trillions of miles away can effectively flip the switch on terrestrial life. The Devonian pulse and supernovae. The late Devonian extinction, 370 million years ago, was a prolonged crisis. Recent evidence suggests a celestial culprit, supernovae. Traces of iron-60, an isotope produced only in exploding stars, have been found in geological strata from this era. This implies that a cluster of supernovae exploded relatively close to Earth, perhaps within 150 light-years. Unlike a GRB, which is a sniper shot, a supernova remnant creates a bubble of cosmic rays that the solar system passes through. This passage could last thousands of years. The result would be a depletion of the ozone layer and a massive increase in muon radiation reaching the surface. This radiation is mutagenic. It damages DNA. The Devonian extinction decimated the coral reefs and the armored fish, but it also coincided with the rapid evolution of tetrapods, the first vertebrates to walk on land. It is possible that the radiation pressure acted as an evolutionary accelerator, forcing life to adapt or die, pushing our ancestors out of the water. The Permian-Triassic extinction and galactic tides. The Great Dying 252 million years ago was the closest life came to total annihilation. 96% of marine species vanished. The primary cause was the Siberian Traps, a massive volcanic province. But why did it happen then? Some scientists propose a connection to the galaxy's structure. The solar system orbits the center of the Milky Way, but it also bobs up and down through the galactic plane. The galactic disk is dense with dark matter and stars. As the solar system passes through this dense region, roughly every 30 million years, the increased gravitational tides can disturb the Oort cloud, sending comets toward the inner planets, and potentially inducing geological stress in the Earth's core. This Shiva hypothesis suggests that the periodicity of mass extinctions aligns with our galactic orbit. While unproven, it implies that the internal geological fury of the Earth might be synchronized with the clockwork of the Milky Way. The Triassic-Jurassic transition and the Manicouagan impact. The extinction that cleared the way for the dinosaurs occurred 201 million years ago. While volcanism is again a prime suspect, a major impact crater in Quebec, Canada, the Manicouagan Reservoir, dates to this time frame. The crater is 100 kilometers wide. While the dating suggests it might have occurred slightly before the main extinction pulse, the environmental stress of such an impact would have been immense. It likely contributed to a cascading ecosystem collapse. The removal of large competitors allowed the dinosaurs, previously a minor group of small runners, to seize the ecological throne. The Age of Dinosaurs was inaugurated by a catastrophe that cleared the stage. The Chicxulub impact, the apocalypse. No event better illustrates the theme of cosmic catastrophe than the KPG extinction 66 million years ago. For over 150 million years, dinosaurs ruled the Earth. They were perfectly adapted, diverse, and dominant. They did not fail, they were murdered. A rock, 10 to 15 kilometers wide, struck the Yucatan Peninsula in Mexico. The physics of the Chicxulub impact are horrifying. The asteroid was traveling at 20 kilometers per second. The kinetic energy released was equivalent to 100 million megatons of TNT. It punched a hole through the atmosphere, creating a vacuum that violently collapsed. It struck a shallow sea underlain by sulfur-rich rocks. The mechanism of killing. The impact vaporized the asteroid and the target rock instantly. A plume of plasma, ash, and molten rock was blasted into space. As this ejecta fell back to Earth, it re-entered the atmosphere, heating up due to friction. For several hours, the entire global sky turned into a broiler. The infrared radiation raised surface temperatures to hundreds of degrees. Forests spontaneously ignited. Animals on the surface were roasted alive. Only those that could burrow, dive, or hide in crevices survived. This explains why no land animal larger than a cat survived. Following the fire came the ice. The sulfur and soot blocked the sun. Photosynthesis stopped. The food web collapsed. The oceans acidified. The dinosaurs, the pterosaurs, the marine reptiles all vanished. The mammals, small and nocturnal, crawled out of the ash into a new world. We exist because they died. The Eocene impacts and the shift to ice. The Cenozoic era saw further assaults. 35 million years ago, the Papagai impactor struck Siberia, and the Chesapeake Bay impactor struck North America. These were massive events, yet they did not cause a mass extinction. This suggests that the biosphere's vulnerability varies. However, they occurred during a transition from a hothouse Earth to an icehouse Earth. The dust and aerosols may have tipped the climate system over the edge, accelerating the formation of the Antarctic ice sheet. This cooling dried the planet, shrinking the forests and creating the grasslands. The evolution of horses, grazers, and eventually bipedal apes is linked to this spread of grasslands. Once again, a rock from space nudged the climate, driving the evolution of our ancestors. The Younger Dryas Impact Hypothesis. Closer to our own time, 800 years ago, the Earth was emerging from the Ice Age. Suddenly, temperatures plummeted back to glacial levels for 200 years. This is the Younger Dryas period. A controversial hypothesis suggests a fragmented comet struck the North American ice sheet. While it left no crater hitting ice, proponents argue it caused the extinction of the megafauna, mammoths, saber-toothed cats, and the disappearance of the Clovis culture. Evidence includes platinum spikes in soil and nanodiamonds. If true, this impact directly altered the course of human civilization, perhaps forcing early humans to develop agriculture as the climate became harsh and game animals vanished. Cosmic rays and genetic mutation. Not all cosmic influences are cataclysmic. A steady drizzle of cosmic rays, high-energy particles from deep space, bombards Earth constantly. This radiation penetrates the atmosphere and can strike DNA. This causes mutations. While most mutations are harmful, some are the raw material of evolution. It is estimated that a percentage of the genetic diversity on Earth is driven by this background radiation. During periods of low solar magnetic activity, more cosmic rays reach Earth. Some studies suggest these periods correlate with bursts of evolutionary change. We are, in part, the mutants of the galaxy. Geomagnetic reversals and solar storms. Earth's magnetic field protects us from the solar wind, but this field is unstable. It flips polarity every few 100,000 years. During a reversal, the field weakens, allowing more radiation to reach the surface. The Lachamp event, 42,000 years ago, was a brief excursion where the field collapsed to 5% of its strength. This coincided with the extinction of Neanderthals and the appearance of cave art. It is theorized that increased UV levels drove humans into caves for protection. Furthermore, the sun produces solar flares. The Carrington event of 1859 was a massive solar storm that fried telegraph wires. If it happened today, it would destroy our satellite grid and power networks, causing a technological collapse. We are technologically vulnerable to the mood swings of our star. The panspermia hypothesis. The most radical idea is that life itself is a cosmic import. Panspermia suggests that microbial life, or at least complex organic molecules, exists on comets and asteroids. We know that rocks can travel between planets. Martian meteorites have been found on Earth. If life started on Mars when it was wet and warm, it could have been blasted into space by an impact and landed here. Alternatively, comets could have seeded the early Earth with the spores of life. If this is true, we are all aliens. Future threats, the Neo-Menace. Today, we scan the skies. we have identified thousands of near-Earth objects, NEOs. While no dinosaur killer is currently on a collision course, the threat is real. In 2013, a 20-meter meteor exploded over Chelyabinsk, Russia, with the force of 30 Hiroshima bombs. It was a reminder that the solar system is still active. However, for the first time in 4.5 billion years, a species can fight back. The NASA DART mission proved we can deflect an asteroid. We have moved from passive victims to active defenders of the biosphere. The death of the sun. The ultimate catastrophe is unavoidable. The sun is heating up. In 600 million years, it will be too hot for photosynthesis. Plants will die. The oceans will boil. Earth will become a dead rock. In 5 billion years, the sun will swell into a red giant, swallowing the Earth. The atoms that make up the pyramids, the oceans, and our bones will be returned to the furnace of the star. This realization gives our current existence a profound fragility and value. Conclusion: the cosmic perspective. The history of Earth is a history of space. The boundaries we draw between geology, biology, and astronomy are artificial. The water in our glass is cometary. The iron in our blood is stellar. The dominance of mammals is the result of an asteroid. We are the children of gravity and radiation. Understanding these cosmic catastrophes is not just about studying the past. It is about securing the future. We are the first generation to understand the cosmic context of our existence. We stand on a blue marble, drifting through a dangerous dark, sustained by a delicate balance of forces, the survivors of a 4 billion year gauntlet. The universe is not a garden. It is a wilderness, and we are just beginning to learn how to survive in it.